Hello, guys. You're welcome to this lecture on the linear second order differential equations. Um, I'm going to walk you through an introduction. Most of it actually will be revision for you guys. This is often a second year or third year class on differential equations. But there will be aspect of it, especially on the theorems that you will need for this class. Okay. So look at introduction, and then I'll move on to homogeneous equations, existence and uniqueness theorems, and then we'll segue into non-homogeneous equations. I'll give an introduction of that. We'll look at the superposition principle, existence and uniqueness theorems, and then the method of undetermined coefficients. I might add variation of parameters later, or I'll just give it to you to study on your own. Okay. So that's the plan. This is going to be a couple of videos, maybe two also to cover these topics. Okay. So linear second order differential equations are equations of this form. A function f, which is often a continuous function of the independent variable or independent variable t. Sometimes it's x. Then y prime, where y here is an unknown function or the dependent variable. Okay, so it's of this form. And we say that the equation is linear in f if y prime, the function f is linear in them. Okay, then we say that the differential equation is linear, and we have an equation of the form 2. So you have a2, it could be a function of t. It's linear also because, I mean, these coefficients are not functions of y, they're just functions of the variable t, okay? And often we assume that these coefficients, as well as the forcing function here, are continuous in some open interval, all right? So in what we are going to do, we are going to look at actually constant coefficient equations where these coefficients here, a2, a1, a0, are constant, so that the equation becomes ay prime plus sorry, by prime plus cy is equal to f of t, where of course a, b, and c now are just constants. So we'll be looking at equation 3 for the most part of this lecture. Okay. We'll look at a typical model. All right. The second order differential equations are often used to model different things. Okay. But one of the most typical applications of the second order differential equations is in mechanical systems. All right. So we have a mass, for instance, attached to a spring with a spring constant, let's say K. And of course, if you pull this, there is a restoring force. All right. If you pull the mass, there's a restoring force that's trying to pull the mass back in the opposite direction. So if you call that restoring force f of r, and assume that that restoring force is proportional to the displacement, which you are calling y, of the mass, then of course we can write the restoring force as equal to negative ky, where k here is the constant of proportionality. All right. So as you pull the mass away from the equilibrium position, let's say y equals 0 here, the restoring force tries to bring it back, and then it is going to oscillate back and forth, right? And so that force that restores it back to the initial position there is what we're calling the restoring force. Okay. K here is of course the constant of proportionality. Is also often called the stiffness. I'll come to that in the next slide. Okay, so this is a setup of the system. Yeah, K is often called the stiffness of the system. And the negative sign is because there are restoring forces acting in the opposite direction to the displacement. Okay. Apart from the restoring force, the system also experiences, it does experience some frictional force or damping force, right? And it can take different forms. All right, the damping could be mechanical, magnetic force, electrical, all kinds of different forces could be opposing the motion. Okay, so we just call it a frictional force. Okay, And often it is usually modeled by assuming that the frictional force is proportional to the velocity, all right, to V here, which is of course dy dt, the velocity of the mass, and it acts in the opposite direction. So the frictional force can be written as negative V multiplied by the velocity, which is dy dt. Okay. Once again, the negative is there because the friction is acting in the opposite direction. If the mass is going this way, the frictional force is opposing it in the opposite direction. Okay. B here, of course, the constant of proportionality, but because this has to do with the damping, we call it the damping coefficient. Okay. Now, as I said, there are other forces. Okay, there are other forces apart from the frictional force. Those other forces, we lump them together. All right, the magnetic, gravitational, electrical forces, and we call them external forces. Okay, so we separate the frictional force from these other forces, and these other forces are just called the external forces. Okay, so so we have a system which is moving, is accelerating, has a mass m, acceleration a. There are different forces acting on it. So we go back to Newton's law of motion that says that force is equal to mass times acceleration, right? So the mass times acceleration is equal to the sum of all the forces acting on it. So that's what we're going to use to come up with a model. All right. And so if you look at Newton's law, where F is equal to ma, we have a mass that's accelerating a. Acceleration is changing velocity with time, or d squared y dt squared. And so we're going to have ma, so mass times acceleration is equal to the sum of all the forces, the restoring force, the frictional force, and these are the external forces. Okay. Fr here is negative ky, so you can bring it to this side. This guy we just looked at, the frictional force, we bring them to the left-hand side. And so we have an equation that looks like this. And so now this becomes the model. Okay, it's a model for the oscillations or the vibrations of the mass being attached to the spring as it moves or oscillates back and forth. Okay, so that is a model for that system. Okay, if the external force that's called E is 0, if we don't have any external forces and all we have is the restoring force in the damping, then what we have is what is called a free vibration, right? If this is 0, we have the free vibrations or free oscillations. But if we have an external force, then the system is said to be governed by the forced vibrations or forced oscillations. Okay, that is when Fe is not equal to 0. So this second order linear differential equation is what governs the motion of the system. And whenever you see a second order equation, of course, you can always think of this mechanical vibration thing, but it also applies to other systems as well. But that gives you a picture of some of the applications of a typical application, I should say, of second order differential equations. Okay. Good. So that is by way of introduction to second order differential equations. Here's an example. Okay, so let's take the equation that we just derived and assume that m is 1, b is 0, so we don't have damping, there's no friction. And then we take k to be equal to 1, okay, and no external force. Then the model just reduces to this simple equation, okay, which we can solve. As I will comment on later on, I'll show you how these are solved. You guys know how to solve this already, but for undergrads, I will teach them how this is solved. Okay, so let's assume that the initial displacement is 0 and the initial velocity is 1, okay? Then it is easy to check that a solution to this differential equation is just given by the sine t, okay? So these are just purely sinusoidal oscillations. And how you check is that you can find the second derivative of sine t and add it to y, which is sine t, and you can check that the result is 0, which shows that this is actually the solution to it, okay, with these initial conditions. Okay, so the vibrations are just, the free vibrations, no damping at all, that are just oscillating. And of course, we know how to plot the sine. If you plot it, it is the black curve, all right? So you just have a sine curve, right? Because the mass is just oscillating back and forth, okay? Back and forth. So those are governed by these oscillations. And the amplitude, because there's no damping, the amplitude remains fixed, okay? It goes to this position, comes back to this position, goes back to the original position. It's not damped. It just keeps moving back and forth like that. No damping at all. Okay. And then we'll show later that these blue and red curves are cases where you have damping. And in that case, the amplitude of oscillation, as well as even the phase, is modified. Okay. So sine t is basically a solution to this differential equation and is given by this sine curve, right? Okay, good. Now, so for this second case, the same example, but now instead of b being 0, I take b to be equal to 1 over 2. Okay, b is just half. And so we've added some kind of damping or frictional force, if you like. And then the equation becomes this, right? Now b is not 0, so we have this term here. So that the equation becomes this. Once again, later you will see that this is easy to solve. When you solve it, you see that the solution to this equation is given by this. Okay. So when you add damping, the solution is modified. It's no longer the simple sine or sinusoidal oscillations. You have a change in the phase, all right? But this is not as important for now. But you also see that there's a change in the amplitude, right? The amplitude is now modified by this term here, okay? And you see that as t goes to infinity, all right, with time, this guy goes to 0 because of the minus. This goes to 0, which means that y in general goes to 0, all right? The solution damps out with time, okay? So the thing is oscillating, but because of frictional forces, it doesn't go all the way to the end. It keeps oscillating and decreasing until it decreases to 0, okay? So that is how the system will behave when you add damping to it, okay? So if you go back to my curve here, the blue curve is what I just described. In the presence of damping, it starts up like the original one, all right? It's going, but because of damping, it doesn't get to the top, right? It decreases. And it decreases to a maximum that is less than the original one. The time it takes to reach the maximum is smaller than the time the original one, all right, without damping takes to reach the maximum. But it reduces and then in magnitude, and then it crosses, all right, the 0 line and begins to decrease in amplitude and decreases, okay? So this is when B is half. In the third example, which is similar to this one, B is going to be 1, all right, which is the red curve. And in that case, it's very similar. Again, because the damping is greater, right? 1 is greater than half. Because the damping is greater, the amplitude also reduces, okay? Much smaller than this one. And then it dampens even faster, right? And goes to 0 because of the presence of damping. So this is just a motivational example, an example to motivate this typical model of the second order differential equations. Okay, so this was the second example. This is the third one I just described. In this case, B is 1, the damping is 1, which is greater than the half, and the solution is given by this. Okay, so the presence of the damping causes the amplitude of the oscillations to decrease with time, as you would expect, right? And this then pumps up, okay? And moreover, you see that the larger the damping coefficient, the greater the effect you have on the amplitude of oscillation, okay? Now, so in the next example, we'll learn, the next section, we're going to learn how to formally, how do you actually solve, all right, these type of equations. Okay, for you guys, this is a revision for you, so I'm going to move through it very quickly. All right. But for others, for the undergrads, of course, I need to be slower with this. But for you, I'm going to move quickly and show you how we actually solve homogeneous second order differential equations quickly. So let's move to homogeneous second order equations. Of course, we have the general second order equation is homogeneous if the external time here, external force is 0. And that gives us the homogeneous equation, which I call equation 8. So whenever you see equation 8, remember I'm talking about the homogeneous equation. Okay? Now, if a couple of things that you might remember is that the identically zero, all right, solution here is always a solution, all right? Y is equal to 0. If you plug y equals 0 here, it satisfies it because there's y everywhere in each term, okay? So the identically zero solution is always a solution of the homogeneous equation, and it's called a trivial solution. Also, if you are given a pair of solutions, y1 and y2, okay, for a second order equation, you expect to have two solutions because second order, okay? You can always form an infinite number of solutions, all right, by constructing these linear combinations. C1 and C2 here are constants. So if I form a linear combination, this is easy. It's easy for us to show that this combination is a solution to this by just directly substituting equation 9 into equation 8. You can show that this is a solution to this. But this is an infinite number of solutions because this is true for all combinations of C1 and C2. Okay, so you have an infinite number of solutions. Okay, so keep this in mind. The fact that the y equals 0 is always a solution of this, and the fact that you can always form a linear combination. Whenever you have two solutions, you can form a linear combination to form actually what is called a general solution for the homogeneous equation. Okay, so that will be the general solution for it. So quickly, how do you solve a homogeneous equation? Some of you have seen this before. First of all, you assume that you have a solution that is of the form y equals e to the rt, this exponential. And then you substitute it into the equation 8, which is the homogeneous equation. When you do that, you get what is called a characteristic equation or auxiliary equation, and it's given by this. Okay, ar squared plus br plus c equals 0. Then your task is to solve this quadratic equation. When you solve it, you're going to get two solutions, two roots, I should say, R1 and R2, okay? And now depending on the nature of the discriminant, right, b squared minus 4ac, you have different kinds of roots and different kinds of solutions, okay? If the discriminant is positive, you get R1 and R2 are real and distinct roots. Then the solutions, your solutions will be two distinct solutions, y1, which is e to the R1 of t, and y2, which is e to the R2t. And so, as I mentioned previously, if you combine the two solutions, make a linear combination of them, you get a general solution, which is given by this. All right? So in the case where the discriminant is positive, you get a linear combination, and this becomes your general solution to the homogeneous equation. Okay? Good. Now, in the case where the discriminant is 0, right, to go back, if this guy is 0, right, then R1 is actually equal to R2, all right? But since we have a second order equation, we need two distinct solutions. We need two solutions to it. How do we get those solutions? All right? Now, if, as I said, if b squared minus 4ac, the discriminant is 0, then R1 and R2 are repeated roots, all right? They are repeated roots. And to repeated root to get two distinct solutions, you have y1 is one of them, which is e to the R1 of t. Remember, R1 is the same as R2, so we could have replaced R1 by R2, or just R, okay? So e to the R1 of times t is a solution. The second solution, to get a second distinct solution, you have to multiply this by t, okay? Your independent variable. Okay, so multiply by the independent variable, that gives you a second solution. And then a linear combination of these two solutions gives you the general solution in the case of repeated roots. Okay, so in the case of repeated root, this is what you get. Good, we'll do examples of these. Finally, if the discriminant is negative, all right, if what is in the square root is negative, then of course you're going to get a complex number here, all right? And so if the discriminant is negative, then R1 and R2 are complex conjugate roots. We represent them by alpha plus I beta and alpha minus I beta. And the solutions are given by, or I'm skipping a couple of things here. As graduate students, this is familiar to you. So If these are solutions, then one of the solutions is given by e to the alpha t cosine of beta t, and the other solution is given by e to the alpha t sine of beta t. And so you form a linear combination of these two solutions and you get a general solution. In the case of complex roots, to be given by this. So you have complex roots, or you get your roots of the characteristic equation, identify the real part and the imaginary part of it, and you can use those to help you form this general solution to the homogeneous equation. Okay, so basically this is the approach, a general approach, a summary approach, if you like, of a solution to homogeneous equations. Okay, good. So let's do just a couple of examples to illustrate this. Okay, once again, I'm rushing through this because this should be a review for you guys. So find a general solution. This should be solution to the following equation: y prime prime minus y prime minus 2y equals 0. B is given by this. C is this equation. We want to solve it. So if we take A, once again, if we assume that our solution is given by this exponential into the RT and we plug it into this equation, we're going to get a characteristic equation, which is given by this, r squared minus r minus 2 equals 0. Well, we can solve this, all right? Break it down, solve it for r. R is given by 2 and negative 1. So you have two distinct roots of the characteristic equation. And so one of the solutions is e to the 2t, the other solution is e to the negative t, right? So if you form a linear combination of them, you get a general solution, which is given by this, c1 e to the 2t plus c2 e to the negative t as the solution. Okay. Then the second example is given by this. This is the differential equation, homogeneous. The characteristic equation is given by r squared plus 8r plus 16 equals 0. Now this is the same as r plus 4 squared equals 0. So if you solve this, you're going to get a repeated root, right? R is negative 4 and negative 4 is repeated. Okay, so once you have a repeated root, one of the solutions is e to the negative 4t. Then the second one, you need to multiply by t, right? So you have to multiply t times e to the negative 4t, and that gives you the second solution. So the first is e to the negative 4t, the second is t, e to the negative 4t, form a linear combination, and that gives you the general solution to the homogeneous equation. Okay, good. And finally, we have this equation here, all right? Once again, form the characteristic equation is given by this. If you solve this, you realize that you get the roots are complex. The roots are 3 plus I and 3 minus I, okay? So our real part is 3 and the imaginary part beta here is 1, right? So you put it in the general form, you're going to have the solution e to the 3t cosine of t, all right, plus c2 e to the 3t sine of t. You go back here, all right, plug in alpha and beta, and that gives you general solution. Okay, so we get a general solution to the homogeneous equation. Yes. All right. Good. Oh, this is the final one. The final one here is an IVP. I have initial conditions. So these initial conditions will help us to find the constants, right? C1 and C2. So we solve it as usual, right? Find the characteristic equation, solve it to get two distinct roots, negative 4 and 2. And so you linearly combine the solutions to get C1 e to the negative 4t plus C2 e to the 2t. That gives me a general solution. All right. But in this case, because I'm giving the initial conditions, I can solve for C1 and C2. Okay. So for the first one, when t is 0, y is 3, that gives me C1 plus C2 is equal to 3. So plug in t equals 0 here. All right. And that gives you that. And then find the derivative of this solution and plug in t equals 0. When you do that, you're going to get negative 4c1 plus 2c2 is equal to negative 4 from the condition, this condition. So you have two equations with two unknowns. So you solve them simultaneously to get c1 is 3, c2 is 0. And so your solution to the IVP is given by this. Y is 3 e to the negative 4t. Okay. So this is just uh, a quick intro to how you solve second order linear differential equations. Okay, in my next video, I'm going to look at the existence and uniqueness theorems, where you have to pay more attention. Okay, so I'll come back, and then in my next video, the um, I'll look at the existence and uniqueness theorems governing the homogeneous second order linear differential equations. Okay. All right. So watch out for the next video on this.